Good afternoon, ladies and gentlemen. Welcome to the plenary session of Faculty of Computing at the 16th International Research Conference of General Sir John Kothalavala Defence University. This year's session is based on the theme of digital innovation for sectorial sustainability and security, empowering a smarter future. And to enlighten us on this topic, we have a very eminent panel of speakers present here with us. Senior Professor Asoka Karunananda, Senior Professor, Faculty of Information Technology, University of Moratuwa, the chairperson of today's session. Professor Yukun Bao, Senior Professor and Deputy Director, Center for Modern Information System Management, Huazhong University of Science and Technology, China. Dr. Ruwan D. Nawarathna, Senior Lecturer in Computer Science, Department of Statistics and Computer Science, Faculty of Science, University of Peradeniya. Professor Thrishantha Nanayakkara, Director of Morph Lab, Professor of Robotics, Imperial College, London. Professor M. Siyamalan, Professor in Computer Science, Department of Computer Science, University of Jaffna. Ladies and gentlemen, before we begin the session, I would like to invite Senior Lecturer Dr. L.P. Kalansurya, Head of the Department of Computer Science, Faculty of Computing, to introduce our chairperson, Senior Professor Asoka Karunananda.
Senior Professor Asoka Karunananda, a Senior Professor of Department of Computational Mathematics, Faculty of Information Technology, University of Moratuwa, Sri Lanka. Professor Karunananda received his first degree from University of Colombo in 1985 and MPhil degree from Open University of Sri Lanka, and he has obtained his PhD in 1995 from University of Kiel, United Kingdom. Professor Asoka began his academic career in 1995 as head of the Department of Mathematics and Computer Science, Open University in Sri Lanka. Professor Asoka has held many academic positions and several managerial positions in the capacity of President, Chairman, Editor, Consultant, and Member. He is indeed an scholar, renowned author, as well as an exponent of artificial intelligence who received many recognition and awards locally and internationally. As a matter of fact, Professor Karunananda is regarded as one of the pioneering scholars in the field of artificial intelligence in Sri Lanka. He also founding member of Sri Lanka Association for Artificial Intelligence, which was started in year 2000. He was awarded Young Scientist Award for Excellence in Popularization of Science by National Science and Technology Commission in 2005 and the Excellence in Outstanding Research Performance from 2005 to 2017. He also received President's Award for Scientific Publication in 2014. Professor Asoka is an important legend for our university as the first Dean of the Faculty of Computing, KDU, and under his guidance, KDU developed all computing degrees under one umbrella, which is indeed an immense achievement as a university of KDU. And sir, because of your vision, we got Best Research Student for 3 consecutive years. In last 3 years, we were able to get Best Research Student in the university. Sir, it's over to you.
Thank you, sir. With that, it is with great honor I invite our distinguished panel of speakers and the rapporteur, Ms. Dharani Abhay-Singha, to the head table. Thank you.
Okay. Good afternoon to everyone. It's really great pleasure and honor to me to be the chairman of this session because Faculty of Computing is my home place. It's a place actually where I took a lot of effort to establish this faculty. I am really happy to notice the uh, and this active involvement of young staff members. Actually, I was basically telling during lunchtime, those crazy boys those days now become big shots in the faculty. So then, with that little note, I have to introduce an eminent panel of speakers for this plenary session. Let me begin with first speaker is Dr. Ruwan Nawarathna. Dr. Ruwan Nawarathna is a prominent figure in academia with an impressive career in computer science, serving as a senior lecturer in the Department of Statistics and Computer Science at the University of Peradeniya. Since 2007, he further distinguished himself by assuming the role of head of the department in 2019 to 2022. With bachelor's degree in computer science from University of Peradeniya and PhD in computer science from University of North Texas, USA, Dr. Nawarathna research proves his excellence. He made significant contribution to real-time medical video analysis during his 6-year tenure as graduate research assistant at UNT Multimedia Information Laboratory in collaboration with Miyako Clinic USA. Dr. Ruwan Nawarathna possesses a substantial research profile primarily encompassing artificial intelligence, deep learning, computer vision. Plenty of his research enters on unconstrained vision models, intelligent transportation system, leveraging biomedical data analytics for health awareness and intelligent video generation. Dr. Ruwan Nawarathna significant contribution have really impacted in the realm of computer science, making him as an exemplary academic and researcher in Sri Lanka. Over to you, Dr. Ruwan.
Okay, good afternoon to all of you. So it's a great pleasure for me to deliver this first plenary talk of this session. So my topic is, as you can see, towards unconstrained computer vision models. So you may be wondering what is this, the unconstrained. I mean, it's a topic confusing. So I hope after 20 minutes you will see what I want to, talk about in this, topic. So, so the computer vision is a branch that empowers the computers to see, understand, and analyze images, just like the human. So that is the catching, term here there. So, as you know, artificial intelligence, I mean, I don't have to give a special introduction to AI. So the things happening outside, right, with the announcement of the large language models, there's a sudden interest among everybody, right? Even our politicians are talking about AI these days. So it is, that much interesting. So computer vision is one of the important fields about the vision. So the humans are so good in vision, right? So computer vision is everywhere in transportation, agriculture, technology, healthcare. So many fields. Computer vision is required. So we all have this wonderful device, the human eyes. So it's amazing device that we have. So it's amazingly beautiful and complex. So let's see why it is this beautiful and complex using an example about human intelligence, right? So if we talk about the human intelligence, if I ask the answer of this one without using a calculator, can you tell? Right? Not really, you struggle, right? How about this one? So can you read this? It's a very, very famous example. So if you, I mean, this is from a language area, of course. I mean, still we can read, right? So it says, do you find this simple to read? Because so, you know, so that is another aspect of the human intelligence. And then some pictures. So, you know, I told you that the human eyes, the human vision is absolutely amazing. So we, in no time, we tell this, you know, this is a monkey, right? It's a monkey image. So, but we couldn't solve that, you know, simple, you see some, you know, 6 numbers, these are 5 numbers, altogether 12 numbers. But see this one. So it's, you know, maybe it's about 40,000 pixels here. But we cannot, I mean, we didn't take, you know, even microsecond to tell that this is a monkey. So that's the beauty of the human vision, right? And I don't know whether you're familiar with this monkey. Is another monkey, right? Maybe this is a famous monkey from US sitcom Friends, Marcel, monkey called Marcel. So those who have watched, you know, Friends know this monkey. Again, in no time they can predict, but you know, some of you, I mean, still just we label this as a monkey, but not as that specific monkey Marcel from the Friends TV series. And maybe with the help of this one, maybe some people will find it easier, the prediction. So you see, I mean, sorry, the pitch is not that clear. You see the cast members of the Friends TV series. And so this monkey is of one of the characters called Ross. If you, you know, if you have seen the Friends, you may know. So, so the first monkey was, it's just a monkey standing on a, you know, tree. The second monkey was a special monkey called Marcel. You know, with a little bit of information, the humans still can come up with an accurate prediction. If you, those who have watched Friends, still, you know, can easily tell this is the monkey Marcel. So this is the complexity of the human vision. It's, you know, wonderfully capable of, you know, predicting things in no time, compared to these kind of tasks that the humans needs help of computers, right? Having said that, now you know, we see the improvement in the camera technology. We have the phones now, iPhone 15 coming out in next week. You will see another, you know, big improvements in the, you know, video technology, the cameras. Having all this, have we done enough in computer vision? Right? Have we done, are computers capable of, you know, doing things like just like the humans, right? So the reason that I included these pictures that, so this is the blind person, unfortunately. So, you know, have we designed anything that give vision to blind people? And have we, now this is, you know, destroying some forest, have we kind of, you know, we have all those drone technologies, right? Drones flying everywhere. So have we able to kind of give a message, oh, this area is being damaged like this? You know, can we alert a parent, your kid is in a swimming pool and about to drown? So, you know, have we achieved that level of, you know, vision? So that's what I want to talk about. So, you know, the journey so far, we have made a lot of strides, and you know, towards achieving the human level vision, right? So let's see more. So this is, you know, a picture taken from a camera, and you know, computer vision is simply converting the picture to this kind of a nice description. You know, a lot of details, you know, identify the objects, right? So this is the Leo, the person called Leo, and we have the high chairs, cake, so those are object detections. And then the phrases like standing on this, you know, Leo standing on a chair, and he is ecstatic, right? He's, you know, happy with his birthday cake or something. So So that is the complete description of this picture. Can our computer vision systems do that? But the humans can do in no time. This, looking at this picture, everyone can say this boy is happy, maybe a birthday, right? So we can easily tell that. But can the computers do the same thing? So that is, we are in the process of, achieving AGI, artificial general intelligence, to achieve that. So we need this, computer vision to, be successful. Machine that exhibits the human level intelligence, Ruwan D AI, right? So, so we are in the process of achieving. So vision is a crucial component. And if we list all the techniques that we use to achieve this AGI, from starting with, machine learning, deep learning, state-related techniques, variable-related techniques, and finally to logic level techniques. For all these techniques to be successful, we need to communicate and we need to perceive and act, right? So that is crucial in achieving AGI. So therefore, vision is really crucial, right? So having, talk about the importance and what we want to achieve with the vision, so let's quickly go through how humans detect objects. So we, focus on these, areas, special areas of the, monkey, and we quickly do some analysis. We, divide them maybe into regions like this, or maybe these are the regions, ROIs, regions of interest of this image, and plus other features. Other features means like the example from the Friends TV series, the monkey muscle, to tell that not just a monkey, to monkey muscle, we need other features. So combination of these regions plus some other features, human brain use its neural network and process it and going to predict that it's a monkey on a tree, right? So that's how the human brain works. And we have been able to come up with a technology called convolutional neural networks about 25 years ago, and then it suddenly came into real AI terminology in 2012, around 10-12. So it can do the same thing. So it can predict as a monkey by just like the human. So the human brain is a very high level device. So we don't look at individual pixel of this image. So we look at very low level details, we quickly process them, and then we go to the highest level, right? So this is the hierarchical learning. So the hierarchical learning was the main technique that the people used over the last 20 years, right? The learning at various levels using this deep learning technology called the convolutional neural networks, and then we are able to predict this object monkey. Quickly going through some of the vision tasks. So one of the tasks is to just assign labels, just like that monkey. So we have to simply assign, okay, the image is there, assign your label. So that is called image classification. But classification with localization is a different problem. So we need to localize as well. We need to show, okay, there is a cat, but where is that cat? So we need to draw some kind of a box we call the bounding box. So that is the image classification with the localization. Then comes the main topic that I'm going to cover, object detection. So we have a lot of objects in the image, and it's about predicting all the objects at the labels plus the bounding box. Maybe go a little
further and do up to the level of segmentation, whether we can do any can we draw the exact boundary of the object. So that is called the segmentation. So we have semantic, instance, panoptic segmentation. So those are the problems of computer vision, right? and the object landmark detection of the human actions, behavior. So this is a very important area, especially in surveillance, in sports video analytics, object tracking. So where certain the path of the object, the trajectory. So analysis of those. Of course, the image captioning. So image captioning requires not only to analyze the picture, but also to predict the right caption. So that includes some language processing skills also. So these are from the popular area these days called the generative AI, text to image generation, given a text, generate an image. Image reconstruction, another application of the generative AI. So I have listed some the important computer vision tasks just to give some idea. So out of these, I'm going to focus on object detection in this talk. So in terms of object detection, when it comes to object detection, to achieve this unconstrained human level computer vision, what we should do. So we have to face these challenges. So what are the challenges that faced by the computers to achieve this human level intelligence? So one of the challenging situations is to do surveillance under adverse environments. So we saw these pictures last year, right, during our protests happened in Colombo, and recognizing these people. So it's a very challenging problem. I mean, recognizing people with certain, maybe a gun or certain, stick, knife. So we need that type of, surveillance, and surveillance on the cloudy days, just the daylight today, without, lack of lighting, fire, right? When there is a fire, nighttime surveillance is another separate area. So we have to overcome these challenges. So another main, big problem in computer vision is this, obscure and, overlap boundaries, right? And also inter and intra-class high variations, just like the food, right? So we humans can tell this is a salad, but see the differences among these pictures. And we call this papadam, but it's a different types of papadam, right? So this is ice cream. So humans are so good, but this, when it comes to this high variation, computers need special techniques. So these are the journey made so far to overcome these challenges. So all these models that I have listed from the 90s, from the early days. So this is traditional computer vision. Viola Jones, HOG are traditional computer visions. From 2012 onward, we see these wonderful deep learning models, vision models, mainly YOLOs, the RCNN, the fast RCNN, and up to the transformers in 21. So the language, the ChatGPT like language models. So those are based on transformers. So people started looking at transformers, applying transformers to vision tasks. So that is that. So if I quickly go through some of the main techniques, another area that we were successful was this data. Now the humans are good because we have data, right? So if we say cat, so we were able to predict cat because we have seen so many cats doing various things. So the computers need the same thing. Fortunately, we have these big data sets from what we call the superstar researchers, technical giants like the ImageNet data sets, and other benchmark data sets like the COCO, Caltech, or open image data sets, and all these things are labeled data set with the class or the ROI, which we call the bounding box. So this is another reason that we see this success in these areas. And if I quickly go through some of the important techniques that everybody should know as a computer science, computer vision researcher, the region proposal concept, where we do the, something similar to how the human processes an image. The important models are the RCNN, which is again based on applying a series of convolutional neural networks for region of interest. So, this replaces the human, neural network. And we have one-stage and two-stage detectors. The RCNN was improved to a fast RCNN, and the fast RCNN was improved to faster RCN. So these are with different capabilities. So added and also efficiency improved, and various techniques are introduced. So because of the time, I will quickly go through. Another technique is the instance level segmentation. Drawing the exact boundary, not just the rectangle, having the exact boundary on the image. So this is the instance segmentation based on mask RCN, right? So this is, in addition to classification, the bounding box prediction, we have the mask prediction. So all these three tasks are integrated into one network. So that's a big achievement, came in 2018. And then this wonderful technology transformers who transformed AI to where we are now with large language models, chat GPTs and things are because of these wonderful technology transformers. So people are using transformers in computer vision also, right? So we have been successful. So this is a kind of there is a competition among CNNs and transformers. And another important model is called the DETR, end-to-end object detection with the detection transformers, another application of transformers. And another technology that you should know should be the YOLO, you look only once. So that is another, so this is called a one-stage, detector. So going like this, if I, summarize the techniques that, the researchers or the, companies use to achieve this human-level intelligence, I can give you this summary, right? With all these techniques, we have been able to come up with successful computer vision models. We are, you may argue we are not quite there just like the language models, but we are, about to get there. In the next couple of years, you see something similar to ChatGPT will come in the vision aspect, right? So these are some of the works I have done in this area with, obscure and overlapping boundaries. We have created our own data set and tested all these techniques that I have mentioned. We are currently working on, in a public surveillance data set, we have created our own data set based on, some of the images are also from the Aragale also, some certain incidences. So, we are working on that. So finally, so I would like to conclude that with this short time, computer vision cannot be discussed in 20 minutes, but I tried best. In summary, so we have seen significant advancement in computer vision, achieving human level intelligence. That means unconstrained, no constraints. Unconstrained with no constraints, just like the humans. And so we have been able to move from these traditional image processing techniques to advanced deep learning, human vision inspired approaches. And these are some of the reasons. So one of the reasons I would like to focus on the superstar researchers. So superstar computer vision researchers, if I tell you some names, the Yan Li, Kun, Andrew Ng, those kind of superstar researchers have made these things possible. So finally, I personally hope to see some really, big model will come in the next couple of years, that human level vision capabilities. So, with that, I will conclude my, plenary talk. Thank you very much.
Okay, thank you, Dr. Ruwan. Okay, actually we have almost 7 minutes for asking some questions and getting any clarification also. Our floor is open for questions and answering. I encourage audience to, shall I ask a question to
Yes,
start?
yeah.
Actually now, all what you said is the fantasy of making the machines are intelligent in terms of vision. I am curious to know whether there are any approaches to improve our vision. Actually, our vision normally go down when we get older. So then are there any techniques now happening at the moment to implant some chips or any other thing to improve our natural intelligence of vision?
Yeah, so that is a good question. That's as I mentioned earlier. I mean, have we been able to achieve that level? So, yeah. As far as I know, there are raw products, but not really up to that level. Yeah. So, yeah. So, good
Yes,
question. Yeah.
okay.
Yeah.
Okay, thank you. Please.
Yes.
Regarding the research happening in the area of computer vision, are you happy about the level that we engage with research in that area, or do you think that we must be much more towards in that?
Yeah, happy as well as not happy, because happy because we have been able to do some work, publish at top level journals with the resources we have now. Computer vision, the main challenge is the machine power. The images, when the number of images exceed at 10,000 to 100,000, then we need the computers. So yes, we have here and there in Sri Lanka, we have the clusters, but not that level of what we have maybe at the Stanford University. So there are a lot of, as far as I know, there is every university there are 3 or 4 doing computer vision research. So there are pretty good, human resources wise there are, but definitely we need more resources in terms of the computing and the, but we have been able to survive with the cloud resources, of course, thanks to Google and the Amazons. They provide this initial, the free quota. So, that has been the lifesaver for our students. So they, go with the Google Colab with the free quota. So most of the time the master level research can be done, but to go beyond that, we need, that, but that is, having said that, that is a challenge for everyone actually. That's why the big technical giants are playing the main role in computer vision, the Facebook, Google, Amazon, because they have the computers, they have the data. So, thankfully they have published this data. I mean, for example, this ImageNet data created by the Stanford University is available to download free. So that was, we have to thank them. So that's what I can tell you.
Good afternoon, sir. So this is a rather unconventional question and not directly related to what you said, but I want to know if there's any full stop in AI, because everyone's talking about AI, it's overhyped, and then everyone's trying to integrate AI into pretty much anything. I mean, using that for a good cause is understandable. Like you said, using it to cure blindness, for example, is understandable and appreciable also. But then again, I came across this news a couple of days ago that they created this robot for boxing and that he defeated the world's best boxer as of now. I mean, are those actually necessary? Like, where is the end point of all this AI and all the technologies?
Yeah, but I think about that is it's true for everything, no? For example, say social media. So do we need a full stop for the social media? And actually we have come to a level now, say Facebook, for example. Initially, at a certain point, we may think that Facebook, I mean, we have to disconnect from the Facebook, but somehow we get back into it, and now the social media is regularized. Facebook has, used a lot of tools to control the various actions. So same thing should be done with AI. So there will be a situation that it will go out of control, but I think we as the research community, I think somewhere in the world, full stop, or maybe the regulatory mechanisms will be applied. But as a person working in this area, still too early to say that. For me, it's too early to talk about a full stop. I think we have to keep going and see, just like for everything in this world, somewhere, some people will come up with some controlling mechanism also.
Thank you, sir.
If there are no more questions, actually, we can conclude. Okay, thank you, Ruwan, for your eye-opening lecture on this computer vision. So please have another round of applause.
Thank you, sir, and thank you very much, everybody.
Okay, we will go to the next presenter today. He is Professor Yukun Bao, Senior Professor and Deputy Director. Dr. Yukun Bao is a full professor at School of Management and affiliated professor at School of Electrical and Electronics Engineering, Huazhong University of Science and Technology in China. His research interests are computational intelligence, based predictive analytics and information system in energy and business. He has been principal investigator for 5 research projects funded by Natural Science Foundation of China. He received IBM Excellent Faculty Award in 2012. He is senior member of IEEE, associate editor of Neurocomputing Elsevier and Journal of Systems and Information Technology, Emerald. He has been named as highly cited scholar by Elsevier since 2020 and was recognized as world best scientist in computer science by research.com in 2022. So over to you, Professor.
All right, so this is my turn to give the research talk. I'm Yukun Bao from China. Actually, I'm from the central part of China. If you look at the map of China, it looks like a clock, right? Actually, my city is in the heart of the clock. Yeah. So my topic actually is kind of application-oriented rather than methodology one. And actually, my slides contain some introductory materials tailored from my syllabus of one course. But here I will read some real projects conducted by my team in the field of energy. We are faculty of computing, right? So computing technology basically have a very potential in a lot of application domain. Just as I mentioned that by the professor about like vision seeing in transportation, a lot of healthcare, a lot of things. And actually energy domain is very important for every society in every country, particularly in China, because we have a very big population. The consumption of electricity, increased year by year, and coal-based energy basically, have some troubles in carbon emission, right? So So how to make it possible to improve the energy efficiency and maximize the benefits of electricity in society's, in human beings' daily life, social, industries developments and economy developments is really, really challenging. So how can computing guys do? What kind of role should we play in facing such kind of challenging of energy? Actually, this is one of the commitments of my center and my team. So here, I just want to showcase some, practice we have done in China. Of course, I will introduce some, conceptual, definitions first. Try to, make it easy to follow, to understand why we was done, what is we have done, and what we will done or something, or we will do something. All right, so when we look at the title of my talk is Big Data and Port Electricity Markets, Data into Assets, and how computing people do for this topic. All right, I'm going to, first of all, to introduce some, definition saying, trying to illustrate characteristics of data in energy industry, particularly we'll focus on, some technical, unique, characteristics of energy-related data. And then we come to know what kind of and what type of, energy-related data available if we want to do something to optimize the dispatch of electricity, to facilitate operating of electricity grid or something like that. And then we come to how. That's to say how computing people like us to do, all right? And I will read some examples of my team's projects. Actually, there's a real projects with industrial partners in China, and we got some software develops, some platform develops, and we also publish some papers to share our experience in algorithms, developments or something like that. And then we come to the end with a open question. So in the market economy so how can we to turn the data into assets by adding up some insightful, analysis with machine learning, computational intelligence or something like that. Okay, so this is outline of my talk. Yeah, characteristic in electricity industry. So by the left side of three-way or four-way, actually, I think you have already familiar with, right? A lot of introductory materials where they talk about, the big data, like four-way, three-ways or something. But I remember you to look at the right side, DEF. And actually, because this is special for energy-related data rather than, general concepts on data. The D here actually about the energy thing. Basically, if we know some, because energy system basically is kind of like a real-time balancing system. Let's still say pour in, pour out must be kept balanced in a real-time mode. So this is the constraints for the usage generation of electricity. So this have some challenges to say, if we have some power or strength, makes the in and outs balanced in real time with some predefined rules, it really can save the consumption of energy. So such kind of data definitely means a lot. Rather than just the data itself, but some economic values. And then we come to exchange. You know, there are lots of stakeholders when you look at electricity markets. Generators, distributors, wholesalers, users, industrial users, commercial users, different types of them. And when we look at energy itself, different types of solar one, wind, power plants, hydrogen power, various sources of energy, you know, the way to generate electricity. So basically, it's come to something like if we can exchange the data from both the supply side and demand side, basically we can do lots of optimization thing, right? To optimize the generation power generation schedule, and to optimize the users, you know, electricity consuming pattern, and try to match them up. So exchange is very important. Then we come to empathy. So how to make the exchange optimized, how to realize it. Actually, we need to look at empathy thing, because by look at the data of like consumption, particularly for consumption side, different industries, different commercial area like some shopping mall or department store, and the different families actually they have different patterns of electricity consumption. So basically, when we look at this kind of, you know, patterns difference, basically we can initiate some policy, particularly use some like economic policy to stimulate the users and guide them, you know, electricity consumption pattern. So basically, a lot of things can be done based on the data. All right, then we come to the what kind of data available so far. Yeah, actually, you know, I guess maybe the same case like in China and Sri Lanka. When we look at the operation of the grid, I mean electricity grid, basically we have lots of data from internal side, like the operation and equipments, generating lots of monitoring data, and then we come to the electricity markets, buying, selling, wholesaling, lots of, you know, transactions in electricity markets. So this always reflects lots of, you know, information behind such kind of trading data. Say we can know some, you know, pattern, particularly for the electricity consumption pattern. And then we come to like power and prices management data about the its operations. And then we can do some optimization, scheduling, portfolio, you know, optimization or something in terms of like investment planning, design, lots of things. Yeah. So at the same time, we have some external data available or needs to be generated from what I just mentioned as the internal data. For the first type of external data is like a geography data, meteorological data, because for such kind of data, it really makes sense about the generation of electricity, as well as the demand, you know, of electricity. And then we come about like environmental data. You might know that, you know, air pollution is really a big trouble in China, particularly in the last 10 years. You know, in every winter, some area of lost China, we really suffer loss from, you know, dirty air. And the main reason for such kind of pollution comes from electricity, I mean the generation of electricity, because of 70% of the electricity of China comes from coal, yeah, the power plants. So how to do some coordination between air pollution control and the production scheduling of power. It's really a challenging. Actually, my team do something. Another is about electrical data, economic data. You know, you might know that the former Prime Minister of China established a unique economic indicator. We call this as like, look at the Chinese economic status by, with insightful insights from electricity data. That's to say, because electricity data, when you look at the consumption of it, you can know how the economy, okay, work. Yeah, how the economy look like. If some sectors, they have a big increase of electricity consumption, it always means that for these sectors, they have some, markets, opportunities. Otherwise, if there are some decrease, you may see some sectors might, declines in the near future. So it's kind of, way for us to look at such kind of external data to know more things behind this. Yeah. And then we come to the third subtopic about how computing work to empower this data to achieve the goals, to get some solutions to the challenges I just mentioned. All right, here we still come to the challenges from three perspectives. One is planning and the design of the electricity system, and then about operation and maintenance, and then training, and see how computing can work. First of all, is about the planning and the design. Actually, this topic sounds like quite micro one, because it has to make some estimates, prediction, or even forecasting, 5 or even 10 years in advance, and then you have to decide what types of energy should we invest, in which place, and how big it should be, the capacity or something like that. So all the things, all the decisions should be based on some data, historical data from demand side and the supply side, as well as some, external data, just as I mentioned, the material data, geographic data, pollution data, environment data, or something like that. Yeah. All right. And okay, because this is not the things we done, so I just come across, and then I will come to the things we do. Okay. And actually, for such kind of planning thing, we need some data to support us decisions in terms of like the consumption pattern of it. That's to say, we need to have some portfolio optimization on what types of energy should we use. And here we do some work with regional state grids branch, trying to establish some model to modeling the consuming pattern for each sub area, and then we decide in which area should be set up some plants and or something like that. Yeah. And here actually this is the map of my province. You might look at the yellow part. Actually, this is my city, the capital city of Hubei province. And actually, this figure tell you about the software we developed to help us to associate the dispatch of electricity with subjects to the environmental regulations. In winter, yeah, particularly in winter, yes, some modeling scene we do. And because our time seems a little bit short for me, another specific topic computing guy can do is about electricity node and the consumption forecasting. And actually this is strength of my team. We have do a lot of things in this area. And just as I mentioned that, I just want to showcase how computing guys to do to make the goal achieved. Okay, actually the core thing is about the predictive analytics. So actually my team do a lot of predictive analytics research based on computational intelligence. Here is just a showcase on how to make electricity node forecasting. Actually, we have do some work in terms of the pulse load forecasting as well as interval load forecasting with the neural network and some heuristic models. Yeah. Okay. Actually, this is an example about the interval values load series that you see. We get a daily, interval for the nodes. We remember the peak one, the highest one, and the lowest one, and make it interval valued in the interval valued form. And yeah, we got this. And then we do some, analysis against the temperature. You need to find the how temperature influence the load, and we do some correlation analysis, and then we get some insights, and then we introduce MA framework, and we select MSVR, multiple support vector regression as a modeler. And by introduce such kind of modeling framework, we can do some interval load forecasting. Yeah. And the smart way, the smart points of the algorithm is that we can do the feature selection as well as the parameters tuning at the same time, by introduce such kind of MA-based schema for feature selection. And yeah, and here is some more details about the performance measure, and we justify our algorithm against in some well-known data sets. And by the MA framework, the feature selection thing, we have a quite flexible outcomes, and which can make its accuracy, prediction accuracy increase a lot. This is the showcase, and this is Australia's data site. And here is the papers published by my group a couple years ago. It's mainly focused on the algorithm developments, and actually in the last 5 years we trying to implement the algorithms into practice. That you say make it be like a software package embedded with some application software, and give it to the discrete operators to use, to make it really make sense to help the decision makers. Yeah, so this is a showcase of that. And then we come back to the open questions, yeah, this is a showcase of the platform my team develops. Unfortunately it's in Chinese, right? But actually this is a forecasting model. Yeah. And all right, then we come to the concluding parts. The concluding parts actually meaning focused on electricity markets. Why? Because in China, we have a very solid, markets economy system to facilitate the electricity markets. Why we choose that markets, because only if we improve or increase the electricity market's efficiency, we can save energy. Energy saving, at the same time, definitely we can reduce the carbon, emission, right? We can achieve the goals, set by the Prime Minister as 30-60. Say in 2060, China can achieve a carbon nutrition, goal or something like that. So it is very important. Actually, this is projects we are doing with some industrial partners by looking at some, electricity trading data and try to do some modeling thing to carefully check the different patterns of from user side as well as the supplier side, and in some scenario like in urban city, or something like that. Yes. So it is very important, for computing guys to work hard, trying to develop some, innovative algorithms to find something valuable behind the data. Okay, that data, really means a lot to us. Thank you. Yeah. Yes, sir.
Okay, thank you, Professor Yukun Bao. Very interesting presentation to me, because I am not a person from anyway electrical engineering, but I am just aware that we are normally considering this, what you call this, generation, then the transmission and distribution like concept in power engineering. So, but I noted that you have some concept like planning, then operation, trading and value addition. So it's the same thing or something different? Actually, I have started the question and answering session. Okay, so then I ask the first question, so then audience will ask the other. So this normal concept of generation, transmission and distribution idea, have you extended that on the planning, operation and so on?
Yeah. In some scenario, real-time balance is the technical characteristics of power system. It must be kept balanced in a real-time mode. So when we look at these constraints, we take it as a constraints when we do some modeling work. Definitely optimization thing, the models, algorithm makes sense.
Actually, in all these
but
stages,
it's very complex because it highly depends on structure of the grid. Different countries maybe they have different regulations on the structure of the grid. In China, we have a hierarchical one, national one, regional one, provincial one, three hierarchy. So when we talk about optimization, we can't do them at the same time. We have to, for example, we use like maybe a national one as a top priority. We take it as kind of constraints. Yeah, and under these constraints, we do some optimization between regional grids. For example, like central part of China, as well as western parts of China. Western part of China, they have a quite, resource for electricity supply. But the local place, their economy is not good. So they don't need that much. But for central parts and eastern parts, they demand a lot. So at this level, and the constraints of national priorities constraints, we do some optimization at the regional level. And the same case happens at like provincial level. Yeah, so it's a little bit complex. Yeah. So actually, I have my team actually at the very beginning stage, we're facing some challenges because when computing guys look at some algorithms, basically we have no idea about the practical constraints. So we just take case in a very ideal case. But when we look at the real case, basically a lot of the constraints, so we have to, find some way translate the complex one into some simple one, and then we do something. Yeah.
Okay, thank you. Audience, if you have any question.
Professor, first of all, thank you so much for the very informative session. Big data, basically the internal and the external data, empower the decision making of stakeholders. However, there are multiple security and ethical issues. So my question is, how can we address these ethical and security concerns when it's come to electricity markets?
You mean the like a privacy or regulation thing? How to,
When we are using internal and external?
I know. Yes, definitely. Some internal data basically is kind of like secrets, or maybe it's confidential. And for the external data, basically because it comes outside, so you can't guarantee the quality of that. You can't guarantee it's real or not. You can't guarantee can't guarantee there is no missing data or something like that. So basically, it's challenging if we take some practical goals as constraints. But somehow, for computing guys, actually we have some, techniques to do something like to handle like noisy data, and to do some privacy, sensitive data analysis. We can do some, pre-processing, and make it, we call this as like say removal, way to make it, transparent to the modelers. That's to say, we possibly have some, technical way to trying, to have some, trade-off. Trade-off. I will use trade-off between, some, interests of the different stakeholders. And another thing is that, because in China, actually, we have a very strong and powerful central government. So, and all the, stakeholders in electricity markets, I mean, not all, but 99% are state-owned. So actually, because such kind of, pattern, I mean, so maybe some troubles or issues, not an issue at all in China at least. Maybe it is an issue in Sri Lanka, but not sure. Yeah.
If you don't have any more questions, so then actually thank you very much for your inspiring talk, because in Sri Lankan context we have a lot of issues related to electricity, especially power generation, because we have only hydropower and thermal power, no other sources available. So anyway, we are still just catching up how the solution can be reached in a manner we will not have this power interruption during the year. Okay, thank you so much. So then we please have another round of applause. Our next speaker is Professor Siyamalan from Jaffna University. Professor Siyamalan holds BSc Honours in Special Degree in Computer Science from University of Jaffna and MSc in Computer Science from University of Nice, France, and PhD from University of Dundee, UK. After completing his PhD, he worked as a postdoctoral researcher at the University of Dundee, UK, and he has authored several papers in high-impact Q1 journals and has received numerous awards. These awards include Presidential Award for Scientific Research, received for twice in the ICT Researcher of the Year 2022 award from Computer Society of Sri Lanka. He has actively participated and won places at several international competitions related to machine learning, deep learning and medical imaging. Currently he serves as Professor in Computer Science at the Department of Computer Science, Faculty of Science, University of Jaffna. Over to you, Professor Siyamalan.
So, good afternoon, everyone. So, first of all, thank you for inviting me for this conference. It's my pleasure to be here. So, today I am going to talk about deep learning with not enough labels. So, here I think in the audience maybe some of you are familiar with deep learning and some of you have no idea about deep learning. Therefore, I decided to divide my presentation into two parts. In the first part, I will be talking about what is deep learning and what are the applications of deep learning, which does not have many technical information. Then I will be moving to handling not enough labels with deep learning, which has some technical information. So let's move to the first part, introduction to deep learning and its applications. So recently, as you know, deep learning has shown tremendous progress. So in the 19th century, researchers were thinking about building intelligent machines. And in 1956, in a conference, the term artificial intelligence was introduced, and from that day onwards, the term artificial intelligence became popular. And by approximately from 1990, the term machine learning became popular, and currently from approximately from 2010, the term deep learning became popular, right? So here, as you can see, there are different terminologies here: artificial intelligence, machine learning, deep learning. So we will see what are they and how do they differ from each other. So if you look at artificial intelligence, it could be any technique which enables computers to mimic human behavior. So these techniques are mainly rule-based techniques. The traditional artificial intelligence techniques are mainly rule-based techniques, and these rules are mainly derived by human experts. And then these rules are explicitly converted into programming. And in this traditional artificial intelligence case, machines almost learns nothing. For example, let's assume this is the program which was which was developed. So this program is mainly rule-based. So now we can give an input to this program and we can get the output. For example, if you look at Dunk prediction, in the traditional case, let's say if high fever and cold, then return no Dunk. Else if high fever and vomiting and not rash, then return no Dunk, and so on. So here, as you can see, this program is a set of rules. So if we give the symptoms to this program, for example, a particular patient has fever, that patient has rash, but that patient doesn't have cold. In that case, if we give this input to the system will tell us the output. So as you can see here, almost there's no learning here. On the other hand, if you look at machine learning has the ability to learn from data. And here we don't have any explicit programming. So that means in machine learning, we are going to specify input and we are going to specify output as well. So the machines should be able to somehow figure out how to map this input and outputs. So finally, we will get the learned model, which is the program. For example, let's say we have two kinds of data here. One is annotated as apples, and other set of data which is annotated as oranges. So these annotations are called labels as well. Right, so we have two sets of data. One is annotated as apples and another one is annotated as oranges. So we will give this data to the machine. So the machine is going to learn the model. So here, as you can see, the machine learning model is going to be y. We can write in mathematically using y is equal to f of x. So here the function f is a complicated function which is going to be the machine learning model. So once we have learned this machine learning model, whenever we give an input to this model, we can get the output. So I am going to talk about a very simple example about how we can do a classification using supervised learning. So that means here we have two sets of data. One set is annotated as apples, another set is annotated as oranges. So we are going to extract some features. So in this particular scenario, as we know, this problem is a very simple problem. So color could be the discriminative feature. Therefore, we will extract color in a two-dimensional space. So here in one dimension it shows orange color, and the other dimension it shows the red color, right? So our feature dimension or the feature space, now as you can see, it's a two-dimensional space. In this feature space, we can see that each image can be represented using a single point. right? So in reality, in machine learning, these feature space are multi-dimensional feature space. So that means it may be even 1,000 dimensions. So in this feature space, we can extract we can represent the images using points. And now we will move to the machine learning classification. So we will learn a classifier which will separate these two different classes. Once we have learned this classifier in the feature space, now you can see we have a trained model here. Right? So now whenever in the testing stage, if we give a testing image, we know that we extract the same features, that we know that where that image will lie in the feature space, and based on that one we can easily classify, we can identify the class, right? So here, as you can see in this particular machine learning classification model, there are two separate stages are there. So the first stage is feature extraction stage, which has no learning there. So based on the human intelligence, based on the human knowledge, we extract, we decide what are the features which are important for particular problem. And then we will move to classification stage, where only the machines learns something, right? So these are two separate stages. In the previous case, so here for the apples versus oranges, we can simply decide what are the features. Color could be the important feature. But in reality, for complex scenarios, like for example, if you want to classify dog versus cats, or even if you want to classify some kind of medical images, benign versus cancerous, in that case, for humans, it would be very difficult to decide what are the discriminative features. Therefore, what we have to do, we have to somehow go for deep learning, right? So in deep learning, the machine should be able to, the system should be able to identify both discriminative features, and it should be able to learn the classifier in a unified manner. So that means in the machine learning case, in the traditional machine learning, as you can see, there are two separate stages are there, feature extraction and classification. The feature extraction stage is mainly handcrafted, so that means human decides what are the features should be extracted, and then we go for machine learning classification. On the other hand, if you look at the deep learning architecture, the feature extraction and classification, both of them are integrated in a unified setting. So we should be able to learn both features as well as classifiers in a unified setting. So deep learning is a subset of machine learning, and as you can see, machine learning is a subset of artificial intelligence. So deep learning is about deep version of artificial neural networks. So what is artificial neural networks? Those are inspired by our human brain. So the traditional artificial intelligence are shallow layers, so they are not very deep, but currently we have deeper neural networks, so that means we may even have 100 to 150 layers. So how to train a deep learning model? So here there's a neural network is given there. The circles represents neurons, and the links between these circles are weights. So that means the interconnection, right? So by adjusting the weights, we should be able to learn the neural network. So here we are going to give an input to this machine, so we can get the predictions based on the current weights, right? So for this particular input, we know the labels as well. So our target is to somehow optimize with this weight so that the prediction will be equivalent to the label, right? So how can we optimize this weight? So let's say these are the two probability vectors, P1 and P2. P1 represents the predictions and P2 represents the actual labels. In that case, we will define a loss function. So here the loss function it's a simple, for example, it's a simple mean squared error loss function. So we will somehow optimize this loss function, or in other words, we will somehow adjust the weights so that the predictions becomes equal to the labels. Okay, so if you look at deep learning, there are multiple applications of deep learning. This figure shows in 2012 in Google, almost there's no applications of deep learning, but in 2015 over 1,500 projects, which includes Gmail, for example, spam detection, auto completion, Google Photos, and those kind of things are deep learning has been used in those kind of applications at Google. If you look at Facebook, again there are lots of other applications like friend suggestions, facial detection, facial recognition, language translation, sensitive content identification, and so on. So there are multiple applications as well. Scene understanding is another application of deep learning, which will be very useful for self-driving cars, robot navigation, blind people navigation, and so on. So if you look at the ImageNet large-scale visualization challenge, it has 1,000 classes. It's a public data set. It has 1,000 classes. Some of the classes are given here, and you can see some of the images from these different classes. So for training, it contains 1.2 million images for training and 100K images for testing. So this is the error rate over year. If you look at 2010, the error rate was around 28.2. On the other hand, if you look at 2017, the error rate has been reduced to just 2.25% using the network which is called squeeze and excitation networks. On the other hand, if you look at the human error level performance, it is around 5%, right? So that means deep learning surpasses humans' performance in this particular scenario, as we have large number of labeled data. So there are multiple other applications as well, image-to-image translation thanks to generative adversarial networks. So here, if we give a female face, we can generate male faces, or even it could be the other way. If we give male faces, we can even generate female faces, and so on. Even in medical images, there are multiple applications like segmenting different organs, identifying different cancer regions, and so on. And as you know, ChatGPT is a revolutionary application of deep learning. So far I have introduced the very basic concept about deep learning and different applications of deep learning. So now let's move to part 2, handling not enough data, not enough labels with deep learning. So deep learning shows state-of-the-art results on various tasks, but if you look at deep learning models, they are usually data hungry. So they usually contains large amount of parameters. Parameters means the weights, right? So here there are different models are given, MobileNet, VGG 16, VGG 19, and so on. If you look at, for example, if you look at ResNet 50, it contains around 27 million parameters, right? So it's a huge number of parameters. So the parameters are the interconnection weights. So we have a huge number of parameters. In order to learn this kind of parameters, we will require large number of labeled data, right? So without labeled data, we can't get better performance. So the deep learning models are data hungry. That means they require large number of labeled data. For example, if you look at a particular classification problem which is called the CIFAR 10 classification problem using the network architecture which is ResNet 50, if we use just 40 images, the performance we can get is only 36%. So if you increase the amount of labeled data from 40 to 4000, the performance improves to 88%. That means we require large number of labeled data. So obtaining labeled data, it's costly, time consuming, it's a tedious process which will require human time, human expertise, and so on. On the other hand, we can relatively easily get unlabeled data. So now the question is, can we somehow use unlabeled data to improve the performance, right? So here we are going to use both labeled data and unlabeled data to improve the performance. That means in this example, we have a set of images which are labeled as cats and dogs. And using those images, we will train a model. So let's say the test accuracy is 60%, right? So now let's assume we have a large scale unlabeled data set. So now the question is, if we use somehow this unlabeled data set to update this model, can we somehow improve this results from 60% maybe to 80%? Right? Can we somehow significantly improve these results? The answer is yes. There are different approaches available for that purpose. So one of the approaches is active learning. There are generative approaches available. There are semi-supervised learning approaches available. So I will quickly go through what is active learning, what is generative approaches, and I will go a little bit detail into semi-supervised learning. So here we can see we can train a model using labeled data. And we have a large unlabeled data set, right? So one way to improve the performance is to somehow annotate this unlabeled data set. If you want to annotate this unlabeled data set entirely, it will require a huge time, right? In that case, what we can do, we can somehow identify what are the data which needs to be annotated, or in other words, we will identify what are the important data or informative data we have to identify, right? So that means we have the model. Based on the model and the unlabeled data, we will identify what are the images should be labeled, a subset of images, and then we will send only that images to the human to annotate. So now we have the labeled data, as well as we have somehow annotated the unlabeled data somehow, and then we can combine simply those two data set, and we can train the model, and we can expect that the model will perform better. So this is one way active learning. There are multiple active learning approaches are there. So recently I was working on active learning, for example, in this particular classification problem, which is called wafer bin map defect classification. So when I use 100K label data, the performance I obtained was 91.8 F1 score, right? On the other hand, I am able to get the same results using only 7,000 images, right? So that means a huge improvement with a huge reduction in the labeling cost using active learning, right? 100K versus 7K. It's a huge reduction in the active learning, a huge reduction in the labeling cost. So next, there are approaches using generative approaches, example, generative adversarial networks or GANs. So here there are some face images are given here. Some images are real images, real person's images, and some images are actually fake images. So that means those images are generated using computers, right? So the ones which are bounding with the bounding box, green color bounding box, are the actual real faces. On the other hand, if you look at the red bounding boxes, they are corresponding to actually no persons, right? So those are fake images. So we can even generate images using generate images under different categories. For example, if you use auxiliary classifier GAN, so there are approaches to generate images from different categories as well. So far we have seen two approaches to handle not enough labels. One is active learning and another one is generative approaches. So now we are moving to semi-supervised learning, right? So this is another approach. So which is an automatic approach, so that means no human is involved here. If you look at active learning, human is involved in the loop, but in semi-supervised learning, no human is involved. So if you look at active learning, there are different categories of active learnings are there. So the approaches proposed can be categorized into pseudo-labeling or self-training based approaches, consistency regularization based approaches, hybrid approaches, and there are other approaches as well, graph-based approaches, generative approaches, and so on. So we will have a look at what are these approaches. So first let's move to pseudo-labeling and self-training based approaches. So in pseudo-labeling approaches, as you can see, we have labeled data, and we have a large unlabeled data. So based on the labeled data, we will train a model. So now we have the model. So we will test this model on the unlabeled data, right? So after testing, for each unlabeled image, we can get the prediction. So now we will select the predictions with high confidence. So that means you can see we will simply apply a threshold on the predictions to select high confident prediction. So that means these two images are selected. And we will use the pseudo labels or the predicted labels as the original labels or the true labels for these images. So now we have the label data and we have the selected high confident pseudo label data, and now we can combine these two as our enlarged or augmented label data to update this model. Right, so how we can train this model, there are two different loss functions we have to incorporate. So the first loss function is based on the labeled loss. So that means based on the labeled data, and the other loss function is going to be based on the pseudo labeled data, the labels we selected. So now we will move to the second category of semi-supervised learning approaches, which is called consistency regularization approaches. In consistency regularization approaches, for each unlabeled data, we can simply go for a labeled loss, whatever the loss we used earlier. Maybe the widely used loss is the cross entropy loss. But for any other data, it could be unlabeled data, we will apply augmentation. So that means we have the original data there, we will augment it. Maybe we can rotate it. If you rotate the image, we can get a new image. If we flip or if we mirror it, we will get another image. and so on. So that is called augmentation. So we will augment it. We will apply the same model and we can get the prediction. Right? So we will apply another augmentation. So here we will apply another augmentation. So this augmentation could be changing the color or brightness, and we will use the same model to predict it. As you can see, we have got two predictions, but for the same image, two different augmentations of the same image. So since these predictions are obtained for the same image, they have to be consistent. Right? So that is called consistency regularization. We have to somehow enforce these two predictions should be same. For that purpose, we may simply go for mean square error between these two predictions, and now we can finalize the loss function. The loss function is going to be the labeled loss function plus the consistency regularization based loss function. So now let's move to hybrid approach. So that means inspired by the success of pseudo labeling and consistency regularization, we have hybrid approaches. So that means those approaches somehow make use of pseudo labeling and consistency regularization. So for each label data, it will be the same loss function. Maybe we can go for the cross entropy loss, but for the unlabeled data, it's going to be different. We will apply an augmentation, we will get an image. We will give it to the model, we can get the prediction. And we are going to calculate the pseudo label based on the prediction. We will apply a threshold and we can get the pseudo label here. We will apply another augmentation, we will pass it to the same model, we will get the prediction. And now what we are going to do, we are going to use the pseudo label we calculated for the first augmentation, and we are going to use that pseudo label as the true label to train the second augmented model, second augmented image. So the loss function is going to be again the combination of the labeled loss plus the pseudo label loss. So usually we apply two different kinds of augmentation. One is called weak augmentation. So that means simply rotations, flipping or mirroring and so on. The other augmentation is strong augmentation. So that means example is cutout augmentation. We simply remove a part of the image and still you can see that is a cat. Right? So we go for this kind of augmentation because weak augmentations are usually far away from the decision boundary. In order to bring the image to the decision boundary, we apply strong augmentation. So there are different other approaches as well. So recently I was working on semi-supervised learning approaches as well. So here for a particular data set, when I use fully supervised learning, I was able to get 97% of accuracy when I use 100% of label data. On the other hand, I am able to get the same results with just 3% of the label data using semi-supervised approaches. So there are multiple approaches available to handle not enough labels. The approaches we have seen here are active learning, generative approaches and semi-supervised approaches. However, there are challenges as well. How to handle imbalanced data, so that means for particular data, for a particular class we may have few samples and for another classes we may have large number of samples. How to apply strong augmentations for medical images, how to handle noisy labels and so on. So there are different challenges as well. Thank you for your attention.
Okay, thank you, Siyamalan. So now floor is open for questions and the discussion. Just to begin with that, actually, I would like to congratulate you for giving this presentation. You started from the very simple model of machine learning, then you came up to this point, and it's very gradual progression of, I think for any student working in the machine learning area, your presentation will be very useful. But actually, I was really waiting for you to talk at least few words about transformer, but you did not. Okay.
Yeah, I didn't include everything here.
Okay. You have any question? Are you working on this area at the moment?
Yeah. Increase the regularization. What do you mean by increase the regularization? Increase the consistency? So usually in consistency-based approaches, we can even go for just random augmentations, and using those random augmentation, we can somehow make them consistent, the prediction consistent. Or there are approaches like mix-up augmentation. So mix-up augmentation, it will somehow mix two different images, and that will become a new image. So there are different approaches are there. We can even go for weak augmentation, strong augmentations, and so on.
So you mentioned that different approaches and aspects of deep learning in your presentation. So as we know, like deep learning is a subset of machine learning. So I would like to know your opinion. What will be the future of machine learning? If deep learning can go up to such an extent, what will be the future of machine learning?
Basically, deep learning is a subset of machine learning, but if you just forget about the neural network part, and if you focus on the loss function or the other techniques, which are quite similar to machine learning, right? So we can even apply the same loss functions using shallow learning, right? For example, we can go for a 2-layer neural network or whatever with the same loss function. So still there are still machine learning is used, but in the future also it will be used, but there are similarities as well, right? So we can't directly forget about machine learning, because the same techniques we are using, I feel the main difference is the deeper version of neural networks. Other than that, the loss function, so here I only talked about supervised learning. So if you look at unsupervised learning, again the loss functions are going to be same, but how we extract the features are going to be different. In deep learning, we extract the features as well. So still machine learning is there.
Okay. If the audience hasn't got any further question, so we go another round of. Thank you. Thank you.